Okay, let's try to understand better what does it mean. What is the meaning of wave dispersion? Okay, so wave dispersion means, for example, for ocean waves, that longer waves travel faster than shorter waves. So I'm going to assume that you already know the basic concept of wave motion. So what is the definition of phase velocity, wavelength, wave, period, frequency of the wave, and so on. Okay. So let's start with an example from a mechanical system. Let's consider a string which is subject to a tension stress T, and let's assume that there is also a uniform bed of elastic springs. So there is an elastic bed with so let's assume this is the direction x, and this elastic bed has a uniform coefficient of elasticity. The stiffness constant basically is alpha per unit length. Okay, we consider this a uniform bed, a uniform elastic bed, and let's assume that at any point x we know what is the elevation, the displacement of the string. Okay, which we call it eta, which is a function of position and time. And and we would like to derive what are the governing equation of motion of this spring. Okay, so and for simplicity, we're going to assume that both the displacement eta and its first derivative are very, very small. Okay, so that's the typical assumption of to make sure that we stay in the elastic regime, and so small fluctuations, and also the slope is also even the slope of the spring is even very, very small. Okay. Said that, let's look at let's consider an infinitesimal element delta x, and let's study the equilibrium of this element. Here the location x, it has the slope alpha, and at the location x plus dx the slope changes. It's going to be now alpha prime. Okay, so you have, and then here we also have the effect of the springs, which are now extended. Okay, and of course let's in general now we're going to assume that the tension at x is going to be different than the one at the other extremity. And now let's apply Newton equilibrium, Newton law. So let's assume these are positive displacements. And what we're going to do basically, we need to decompose these forces, because remember that here we have the effect of the elastic forces. So the spring is displaced, the string is displaces positive in the positive direction. So the action of this elastic spring will be with a force going downward, which has an amplitude alpha eta dx. But then if the string is also accelerating in the positive direction, there will also be an inertial force. This is minus, equal to rho, the length of the spring, minus rho dl eta dot. Okay, and we can assume that the string has very thin, that we neglect the mass. Okay, so so the dominant forces are the elastic ones. Okay, and the inertia. But now we need to understand, we need to also understand what is the effect of the tensional forces induced by the tension at the extremity, okay, which is constant. But let's see how it does distribute along the string, okay? So we already know that this is alpha prime, so I mean, we just have to simply do the decomposition of these forces. This is T2 cosine of alpha, this is T2 sine of alpha prime, and here we're going to do the same things. This basically is going to be minus T1 cosine of alpha, and this is going to be minus T1 sine of alpha. So the equilibrium in the x direction is going to tell me that minus T1 cosine of alpha has to be equal to this is cosine of alpha prime, this is sine of alpha prime. Okay, so we have minus T sine cosine of alpha, this is alpha, minus is plus T2 cosine of alpha prime has to be equal to 0. And the equilibrium in the vertical direction is telling me that what? Is telling me that T2 sine of alpha prime minus T1 sine of alpha minus alpha eta dx minus rho dl. What is dl? dl is very easy to compute because it's the square root of dx square plus d eta x square dx square times eta dot dot has to be equal to 0. Because now the length here, I can compute it as this difference here is basically eta x dx. So I'm going to do delta x square plus eta x square dx square. Okay? So, but now we're going to assume that the displacements are small and also and the slopes. So that is the assumption for the small to be in the elastic regime. And this what does it mean? It means that if we're going to assume that eta and eta x are really small, it means that tangent of alpha, which is also equal to d eta dx at x, is also very small, and so I can approximate it with basically the angle itself, alpha. And so the same things for tangent alpha prime. This is going to be equal to d eta dx at x plus dx. It's going to also be equal to alpha prime. Okay? And so with the tangents we are fine. And so what does it mean? It means that we can basically approximate alpha with the tangent. Okay? Which is basically equal to d eta dx. So, and that's is a very that's what we need, small strain. Okay, that is the assumption. And let's see how these equations simplify, because let's write them. We're gonna have let me review it here. So the first equation is going to be minus T1 cosine of alpha plus T2 cosine of alpha prime equal to 0. Okay. Then the second one is the most important, the one that we are interested in. Plus minus T1 sine of alpha minus alpha eta dx, and then I have this minus rho dx square root of 1 plus eta x squared eta dot dot has to be equal to 0. Okay, so I pull out delta x squared outside, so I'm left with this, and of course this guy is computed as x. So since alpha is also very small, I can Taylor series all this coefficient. Okay, so the first equation becomes minus T1 1 minus alpha squared divided by 2 plus T2 1 minus alpha prime squared divided by 2. And this guy has to be equal, and this has to be equal to 0. So let's work out this expression first. So now alpha is basically the slope, okay, which is this is basically minus t1, 1 minus eta x squared divided by 2 plus t2, 1 minus eta x squared divided by 2, ma computed at x plus dx. Okay? But these are, of course, this guy, we can write it as, we can do further Taylor series, with respect at x plus dx. But it really doesn't matter. There is no need to do it because these guys, they are really, really small by assumption. So we can neglect them, and we're going to get immediately t1 equal to 2. Okay? So as long as we have small displacement, small, angles, so the stresses are, the tension is uniform along the string. And that's nice, and so that's why we can call this equal to t. Okay, let's see what happened now instead to this other equation, which is going to give us the main dynamics. Now we know that t2 is equal to t1 is equal to t, so we can do a further simplification. So we're going to get t, which multiply sine of alpha has become alpha prime minus alpha. Oh yeah. So here there is a problem. I messed up the coefficient. Don't confuse the elastic constant alpha. If it's okay with you, let's call it beta. Okay, because I don't want to confuse it with the angle. So let's call it beta. And so here these things become all beta. I'm sorry. Okay. So let's not too big of a deal. So we can always fix it. So there was a confusion. Okay, so beta is the elastic constant of the spring, of this elastic bed of springs. So here it means that in this equation this is beta. Okay, and now when we try to simplify this equation, this is beta eta dx minus rho. Even here we can neglect this guy, we don't need it. It's very, very small, so this is simply dx eta dot in time has to be equal to 0. But alpha is nothing else that the slope d eta dx, and so we have t of d eta dx at x plus dx minus d eta dx at x minus beta eta dx minus rho dx eta dot equal to 0. Again, we can do the Taylor series of this guy, of the first derivative. So we get t, which multiply d eta dx at x plus the second derivative of eta x squared at x dx minus d eta dx in x minus beta eta dx minus rho dx eta dot equal to 0. So this and this simplify, so we are left with t eta xx dx minus beta eta dx minus rho dx eta dot equal to 0. dx and ds simplify, so to leading order the Copernic equation is given by t eta xx minus rho eta dot minus beta eta equal to 0. So we basically get the elastic wave equation, okay? So because we have this, for beta equals 0, we would have simply the wave equation, okay? So, and this is very known, okay? So, nothing new. So let's understand a little better this equation, and we see that we have, let me change sign. We'll have rho eta dot. Rho basically is the density per unit length of the string, minus t eta xx, the second derivative, plus beta eta equal to 0. Okay. So let's assume now that we have we have an elementary wave, which is of exponential type, kx minus omega t, and we would like to see what are the conditions for a, k, and omega to satisfy this equation. Okay? Since the equation is linear, we already know that the amplitude doesn't matter, so the amplitude can be anything. The most important part is understanding what will be the coefficient k and omega, and to do that, so let's compute the second derivative. The second derivative is going to be basically minus I omega squared times a e to the I kx minus omega t, which basically becomes minus omega squared a e to the I. Let's call this guy theta, okay? So without bringing out, carry out in all these calculations. And the second derivative in space is simply equal to I k square a e to the I theta, which is equal to minus k square a e to the I theta. So we plug those expressions there, so we're going to get rho minus omega square a e to the I theta minus t, which multiply minus k square a e to the I theta plus beta a e to the I theta has to be equal to 0. So let's pull out a e to the I theta, and I'm left with what? With minus rho omega square plus t k square plus beta equal to 0. Now, in order to satisfy this answer, will be a solution of our original equation if this expression is 0 for any x and t. The dependence on x and t is basically in this theta, which is equal to kx minus omega t. And the only way to make these things equal to 0, or you choose a equals 0, and that's basically the trivial solution, which we don't care, or you impose that the entire terms within parentheses are sum up to 0, and that's lead to a dispersion wave condition. So we can impose that rho omega square minus t k square minus beta is equal to 0. Okay? So you see that here we see that in order for the solution to, in order for this answer, in order to have a propagating wave through the string, the frequency and the wave numbers, they need to satisfy this relation. Okay? So let's understand a little bit better this relation, and from this relation we can derive omega squared is equal to t divided by rho k squared plus beta divided by rho. Okay? Which means that omega squared divided by k squared is equal to t divided by rho plus beta divided by rho k squared. And this guy we can write it as omega over k squared, and this is nothing else than the phase velocity squared, which is equal to t divided by rho plus beta rho over k squared. So the phase velocity depends upon the wave number k. Okay? Actually, if we plot this relation, so Cp is a function of k and is equal to the square root of t divided by rho plus beta divided rho k squared. So we see here that when k tends, so if we plot this expression as a function of k, so we have a limiting value, which is basically t divided by rho, which is the speed when there is no elastic bed. And then, the velocity become, so the phase velocity, depend upon k. You see that asymptotically tend to the speed that we would have if there would be no elastic bed that, introduce extra stiffness. And this basically makes sense. You see, it's very interesting. When k is very, very small, the phase velocity become much larger than the one in disturbed spring. Okay, it's the string. Instead, when k is very, very large, so the speed will be roughly the same as the one without elastic bed. And this is very easy to understand because when my elementary wave has a very long wave number, so this length L is basically 1 over k, which is very, very large. This corresponds to k very, very, very small. You see that all the elastic springs, they are all acting in the same direction. They are trying to pull down, so they're gonna basically make the string stiffer and stiffer, and that will induce faster frequency of vibrations, and so larger phase velocities. Instead, when you are in the other extreme case, in which you are doing the perturbation as a very small wave number, which is very, very, very small, which means kk is very, very large, you see that the effect of the springs, here basically the springs are extended, and so they pull down, but here they push up. The total effect basically cancel out. So when k is very large, the effect of the elastic bed is basically null. Instead, it's going to be fully active, for perturbation that are very long in amplitude. Okay. So this is simply just an introduction to appreciate what is the physical meaning of wave dispersion. Okay. Now, what I would like to do now is the Hamiltonian